Okay, so last time we have studied a few quite general properties of operators, and then I say that if we have an operator, if you have x, right, and then you can also have x squared, and or x to any power. Okay, you can even have a function of x that can be written as v0 plus v1 over 1 factorial x plus v2 over 2 factorial x squared, and so on and so forth, right? So this way you can translate potential, the potential Vx in classical mechanics, to an operator, okay, in quantum mechanics, right? So you can just do this very simple translation, okay? You can also have a momentum operator, right? And like this one, or you can have also a function like this, and this one. So then you can, for example, translate the kinetic energy, okay, in classical mechanics into a kinetic operator that is p squared over 2m in quantum mechanics, right? And similarly, you can have the Hamiltonian. Now that equals k plus v in classical mechanics, right? You can do the translation, have the Hamiltonian, that is right. So all of this one seems to be quite good. You can do this one, do the translation, okay? But there's one thing you should pay attention to, okay? And the order is important. Sometimes this translation is not very much concerned with the order, right? But in some cases, you can involve a mixture of momentum and position in classical mechanics. Well, you don't really worry too much about the order, right? Because in classical mechanics, the momentum and the position, they actually commute. But when you do the translation, there will be some difficulty. I'll give you one example, okay? Let me give you one example, okay? We know that in the classical electrodynamics, we have a Hamiltonian, the energy, okay, that equals the momentum P is a vector minus the charge of electron, that's minus, so we can put a plus right here, and the vector potential, okay, and divided by C, and then do this one squared over 2m, right? But you know that in general, this A, so this is actually is a particle in the magnetic field. Okay, so that's a Hamiltonian for particle in the magnetic field. But if you have a magnetic field, this vector potential actually is depends on the position, right? And in this case, you do the dimension, you do the square. That actually means the product of this one, right? Okay. And then you're gonna have some trouble. Okay. So what do we mean P and A? Then you're gonna have if we do the expansion of this one, this is P squared and plus 2EC and A dot P, right? And then plus E squared over C squared and A squared over 2M. Okay. If we do the translation, you can see that this one is okay. So if you do the translation to quantum mechanics, okay. And you should suppose you should have P squared, and the last one is also okay. But then you're going to have a problem because this one is a function of position. This one is momentum. So you can have different choices. You can have, for example, 2A dot P, or 2P dot A, or A dot P plus P dot A, right? So which one should be correct? And so in principle, this actually is not determined, right? So you have three choices. You can put A in front of P, you can put P in front of A, you can put a symmetrical combination. That means A dot P. Actually, you know, if you really want to if you want to be hair splitting, and you actually have an infinite number of choices, right? So actually have in classical mechanics, A dot P equals to P dot A equals to square root of P dot square root of A times square root of A dot square root of P, right? And they are equals to P dot A 1/4, A dot P 1/4, P dot A 1/4, A dot P 1/4. So there are many choices. Okay. Which one is correct? How do we choose this one? Okay. And so actually, there's no way to have a priori determination of this order. Okay, you could be anything. But then of course, someone could argue that maybe the most symmetrical one, the simplest one, is just we say that A. You can guess, right? For example, A dot P, just written as A dot P plus P dot A. That looks quite nice, right? So we can guess whether this one is correct or not. So then we just do the translation. Okay. And what we need to do is to compare this one to experiments, okay, to see whether this one is correct or not. Okay. And then check by experiments. Okay. So you can do the calculation for different properties and look at what's the prediction for the first choice, what's the prediction for the second choice, and then you do the measurement, design an experiment that can tell the difference, and find that this one actually is the one that we should choose for the reality. Okay. But you can say, in general, there could be difficulty, right? If you have a mixture of momentum and position in classical mechanics, and then the translation to a quantum problem, so the order actually could be important, right? So this translation is not that straightforward, okay? But very often, you do some kind of isosthetic analysis, and then make the choice and compare the experiments, and it turns out they're quite correct, okay? But there's nothing guaranteed, okay? And then an important combination is the angular momentum. Classical mechanics, we know that this is just the position across the momentum, okay? And you know that fortunately, all of these terms, for example, Lx will equals ypc minus zpy. And very fortunately, and y and pc and z and py, they commute. So that means the order is not a concern at this case, okay? And then you can have the cyclical of these indices, so that you can have the definition of other terms. Okay, so this gives us the three components of the angular momentum, right? And then you can also define the total angular momentums, okay? Okay, so that's what we have done for this, naive translation of classical mechanics into quantum mechanics. Okay. All right. Okay, so in quantum mechanics, all the quantities are operators, especially a Hamiltonian operator. And then for the operators, the important thing is find the eigenstates. Okay, for example, you have Hamiltonian, And then you can have states plus x equals to E plus x. Okay, so this is the time independent Schrodinger equation, right? And this E is the eigen energy. Okay, and this percent, if we put a percent for E, okay, for this particular E, is the eigen function or eigenstates. Right? And then we know that this time-dependent Schrodinger equation comes from this time-dependent Schrodinger equation, right? From that one, we know that the evolution of this one is actually, we have a separation variable. So this is the dependence on the position. And there's also dependence on time, okay? That's e to the minus I times energy E times T divided by h bar, right? So this is evolution, okay? And notice that this one is a phase factor independent of x, okay? So because of this one, we'll say that this one is actually a stationary state. And to show this, let's do the measurement, right? So let's, to demonstrate the one, let's check by measurement. That means suppose you prepare the state, okay, and you do the measurement, and do this one for x or p or any physical quantities, so on and so forth, okay. Let's just consider x and p first, okay? And let's explain how this measurement should be done, okay? Okay, so this is important, okay? So the measurement of x at t, okay? And how do we do this measurement? So actually, the step one, you prepare the state. The particle in state of percent E x. Okay, so this is a copy. We call this one copy, okay? And then you let it evolve for t, okay? And then the state will becomes percent E xt, right? So that seems to evolve for freely, okay? Okay, you should make sure this one evolution is freely, okay, on the Hamiltonian. Don't do anything on this state at this point, okay? And then the third step, you measure x, okay? Measure the position of the particle. Okay? So at this point, after you have done the measurement, in quantum mechanics, if you do the measurement, actually the state will be changed, okay? Will be in a different state. So then you shouldn't do the measurement again, okay? So that's something very different from classical mechanics, okay? Okay. So this one is important. This is different from classical mechanics, okay? So if we have done the measurement on this x, the state would have been changed by this measurement. So that means you cannot do this measurement of x again, right? Because if we do the measurement of x again, you are measuring the particle on a different states, okay? So that means in the fourth step, you need to just throw away the copy. Okay. So this one, you finish the preparation, evolution, measurement of a copy. And this copy should be thrown away, shouldn't be used again for doing the measurement of X. And then you should continue this one. Okay, repeat. So you should repeat this one many times from 1 to 4. Okay. So this is something that you really have to keep in mind. Okay. So then you basically, so measuring of X on many identical copies. Okay. So you got different results. You get a, a set of outputs. X1, X2, X3. You have many XM, right? So the average, the expected value, of course, we have done this one, is just a summation of all of this one. Okay, so that equals to 1 over m, summation of I and pi xi, right? Sorry, there's no 1 over n anymore. And then the variance that x squared equals to x squared minus this x squared, right? So that equals to 1 over m, summation of xi squared minus this x squared, right? Okay, so that's the way. Okay, so you need to have many copies, identical copies. That's important. Okay, identical copies. And do this one, and then you can do the statistics. If you just do this once, you cannot get the expansion value of X. Okay, that's important. You need to do this many times on the identical copies to get this expansion value. Okay. Okay, with this, let's check the measurement of this state. Okay. Right. So if I have a state. Okay, like this one. Let's look at the average or the expected value of position. We know that this one equals to px dx and times x, right? So that's the what we have learned from this Born interpretation. Okay, so you put this p into this one, you have x per se complex conjugate e x t and per se e x t dx, right? And now you can see that this one is a phase factor that does not depend on x. So when you do this complex conjugate, they actually cancel each other. So this is nothing but just x per se e x and per se e x dx. Okay, right? So that means this one is the same as. So the measurement of this one at different time, okay, actually will give you the same results of this one. And similarly, so if you follow the same procedure, you must have this one. The average of x squared should also be independent of time, right? Okay. So if you put this one, if the particle is prepared in the eigenstate, okay. So this also means the variance, okay. Uncertainty is independent of time, okay. Right. So this is for the, of course, for the position, okay. And how about the momentum operator, okay? Let's look at the momentum operator. We have known that this one, of course, you can do the Fourier transform, okay? Sorry. Okay. You can also do another way, okay? Let me do this one first, okay? We know that this Fourier transform will be just 1/√2 pi per psi e xt e to let's say minus I kx dx, right? So that is the the Fourier transform. But this one, is different from the x0 only by phase factor. So it can be written as this phase factor does not depend on the position, so it can be put outside of the integration. So what's the inside is going to be just simply this one, right? Okay. So you can see that, of course, this one is going to be it's nothing but just per psi tilde k times e to minus I e t over h bar. Okay. So this one is a phase factor independent of k, right? Okay. So it's also, we call this one a global phase factor. Okay. So this one is a global phase factor. So you can see you put this back into this one, so immediately you obtain this. And similarly, the square of momentum, the measurement of this one should also not depend on the time, okay? And so that this uncertainty of this momentum measurement is also independent of time, okay? Right. Okay. So you can see that this one, give us the results of the measurement of x and p, and their invariance. Okay, they're all independent of time. Okay. Before I proceed, let me give you another derivation. Okay. Another derivation is like you can write down this average of this one. We know that it can be written as per psi complex conjugate. And this one can be replaced with the h bar of I d over dx. Okay. Right. And again, you can see that this one is an operation on x, but the global phase factor here, does not depend on x, so it can be moved outside of this operation. So that means that they cancel each other. So this one obviously just equals to per psi e x h bar I d over dx per psi e x and dx. So this is x. So this one is independent of time, right? So you can do this one the same for for the momentum, okay? Right, so that's another way, okay, to prove this. And you can say, now how about the other quantities, right? So you can do the same thing for all other quantities, okay? So the same for example, you can have x force power if you want, or you can have you measure the potential, for example. Okay, so all of these things. So any combination of this one, you can see that you can have percent xe xt. You put any operator right here, okay? Actually equals to percent e x a percent e x dx, right? Because the global phase factor they're cancelled, okay? Right, if we do the complex conjugate of this wave function, and then times the complex conjugate, so you can see that the global phase factor always cancels, okay? Right, so on all of this one, so you can see that if you do any measurements on this state, on many copies, let me evolve from t equals 0 to t, okay? From the same initial state. And then you find that the measurements, no matter what it is, the statistics are always independent of time, okay? So this one gives us the reason to call that the percent E xt, or the eigenstate of H is stationary. So this is important. Okay, remember Bohr's, so recall Bohr's atom model. Bohr these states, that's stationary. That's not changing with time for any physical quantities, so that it's stable. And you can see that the eigenstates, the eigenfunctions of Hamiltonian, okay, satisfy such kind of properties. So they are stationary states. So that makes the Hamiltonian operator particularly important in quantum mechanics. Okay, because once you find the eigenstates of a Hamiltonian operator, you actually find the stationary states of the system. The states that the system will stay for a long time. Okay, that's a good point to pick up questions. Let me say, does it mean that the global phase factor cannot be measured, which is the use of the factor then? This is a very good point. You are right, the global phase factor is not measurable. But if you have a superposition of two states, will be different. Now let's look at to answer this question. This question actually is an excellent question. Okay, and then what's the point of there was a point of this kind of phase factor, right? This will be important, okay? But the phase factor is important in superposition. So in quantum mechanics, a very important thing that we can have a state that's not in a single possibility, but in a superposition of different possibilities. You can have a state percent x equals to percent 1. That's one eigenstate plus. So you can put a coefficient right here. Let me just write that this way, okay? Okay. You can have a say like this one. This is so we have, suppose we have psi m x equals to em psi m x. Okay, so these are the eigenstates. You can have a superposition of this one, for example. Okay, and now you can see that if you have this one, the evolution that will be different. Okay, so this one can be written as psi 1 e to minus I e1 t over h bar plus psi 2 e to minus I e2 t h bar. Sorry, let me. E1 minus I E1 minus E2 over h bar times t, right? And plus psi 2. And this minus I E2 t over h bar. Okay, so this one is global. Okay, we know that that's not important. But this one is a relative phase factor. So this relative phase factor actually changes with time, and it's important because it determines the interference. Okay, and let's do the calculation for x again. See what will happen. Okay, let's do the calculation for x. You know, we do the measurement of this state at the time t, and then we know that this one will be psi xt complex conjugate and x psi xt. Do the integration of x, and you know that this global phase factor will be just cancelled. So what you need really to care about is something like this one, psi 1, okay, e to minus I E1 minus E2 over h bar times t plus psi 2, right? And take the complex conjugate, and x and psi 1 e to minus I E1 minus E2 over h bar times t and plus psi 2 and dx. And now you can see that you can have this term combined with this term, or this term combined with this term. And they are just the same as what we have done before. So that will give us, you know, psi 1 complex conjugate, psi 1 and x dx, and the plus psi 2 and psi 2 and x and then dx. Okay? But you can also have cross terms. You can have cross terms. You can have this one goes with this one, or this one goes with this one. And these two terms are complex conjugate. So if you write down them, you actually have psi 1 complex conjugate and psi 2, okay, times x e to I E1 minus E2 over h bar and t. And another term is just the complex conjugate. Do the integration of this over x. Okay. And this one is, let's say, just psi 1. We just copy this. You just copy this one, okay? Psi 1 x dx plus psi 2 complex conjugate psi 2 x dx. Okay? And then now you have a new term. And this term, now you can see that there is 2 times the real part of psi 1, psi 2, and x e to I E1 minus E2 over H bar and T. Okay, so this one is a phase factor, depends on time. This one we can have have a notation of this one. Okay, let's denote percent 1 complex conjugate x percent 2 dx. We call this one x1 2. Okay, right? And you can see that the percent 2 complex conjugate x percent 1 dx that equals x2 1. That of course is just x1 2 complex conjugate. Right, so you can see that this one, x1, 2, and x2, 1, they are just like they are complex conjugate of each other. Okay, so with this, now you can see that you can also have this one, right? You can have percent 1 complex conjugate x percent 1 dx. You can define this as x1 1, right? Of course, you can in general you can define percent m x percent m dx as x mm. Okay, so now this can be written as x11 plus x22 plus x12, e to I e1 minus e2 over h bar t, and then plus x21 e2 minus I e1 minus e2 h bar and t, right? So this can be written as x11, x22, and then plus 2 times the modulus of x12, and then cosine function e1 minus e2 over h bar and the t plus a phase factor. And this phase factor, of course, is just the phase angle of x12. Very nice. So 1, 2, define this one as E1 minus E2, okay, over H bar. Or you say that E1 minus E2 equals to H bar omega 1, 2. What's this? This is a beautiful term, right? This is the frequency of a transition of an electromagnetic wave emitted by transition between the state 1 and state 2. Okay, so you can see that so we obtain something really beautiful. That is okay. So this one is Heisenberg's oscillator. Say the frequency or the angular frequency omega m just equals to em minus em over h bar. So it's oscillating. You can see that if you have a superposition of this one, you actually have oscillating. Okay, so superposition leads to quantum interference. Okay, right? This is an interference term. This is an interference term, right? Okay. So if you have a superposition of two energy states, you can have and the interference and oscillation. That is to oscillation. Okay, with frequency given by energy difference. Okay, so if I have a large energy difference, okay, that leads to fast oscillation. something we have seen from this one, okay? And there's also another interesting thing, okay? You know that if you have this kind of oscillation, and this one will cause the radiation of electromagnetic wave, right? Okay? But you can say that this xmm equals to percent m x and x percent m x dx, right? This one will be 0 if percent m and percent m are both even or all the functions, right? So what does this mean? So that gives us actually a selection rule. No transition between states of the same parity. That means they are either both even functions or both all the functions. Okay, so you can see that we see a number of interesting things, right? Okay. Right, so this is what I would say that the phase factors actually are indeed important. Okay. If we have a superposition of different states. So one special case actually is the wave packet. And remember, we have a wave packet percent xt that can be written as percent tilde k e to ikx minus I e k t over h bar, right? And the d k. Okay. So this is something that we have derived earlier, right? So you have wave packet, and this one, of course, is moving, right? Okay. So instead of oscillation, in this case, and this movement actually is due to interference between okay, so this is because of the interference between many states of different energies, okay? Right, I can see that the group velocity is given by partial ek partial k times h bar, right? So what does this mean? That means if you have, for example, this is k, this is ek. So if you have something like this one, for example, or if you have something like this one, so from this one you can see that this has, this is case 1, this is case 2, okay? So you can see that in case 1, delta E is larger, right? Than 2, right? For the same delta K. Right, so you can choose, this is K1, this is K2, so this is delta K. I can say that So this is delta E, okay? Or this is delta E, right? So you can see that in the case 1, delta E is greater than delta E in the case 2. So that means the change of the first wave packet, or the wave packet in the case 1, will be faster, right? We say that if you have a larger energy difference, you're gonna have faster changing, okay? So that's means the group velocity of 1 should be greater than the group velocity of 2, right? So now you have another way to understand this group velocity. So it's because of interference of different eigenstates that have different energies. So if you have a larger dispersion, that means this energy difference between two states is larger. So that means it's going to move faster, okay? So that's why the group velocity is given by partial E over partial K, okay? So that's you know, the understanding of this eigenenergy states. They are stationary states. The superposition are, you know, oscillating states. If you have discrete states, if you have a continuum, the superposition states is a moving states. Okay, but anyway, the quantum interference between states of different energies will cause the state to change with time. And if you do the measurement for x, they will be different. Okay, so you can also simulate for x squared and p squared and etc. Okay, so you can do this for other states. Okay, so now let's take a break and see if you have questions. Okay, you can just feel free to